Imagine you're on a carousel that never stops. You can't get off. You can't slow down. You're trapped in endless rotation until the universe dies. We already are. The sun drags you around the galaxy at 500,000 kilometers per hour. And when you zoom out, you realize the sickening truth. There is not one stationary object in the entire cosmos. And here is a question. If you could break one law of physics for a day, which would it be? And what would you do? Let me know in the comments. I will pin the most creative answer. Now let's begin. The story of spin begins almost 14 billion years ago, in the first fractions of a second after the Big Bang. Imagine the entire universe compressed into a space smaller than a single atom, filled with unimaginable energy. Then, in an instant, everything exploded outward. But here's what's fascinating. Even in those earliest moments, the universe wasn't perfectly smooth. Quantum fluctuations, tiny, random variations in density and energy, created slight irregularities in the fabric of space itself. These weren't big differences, but they were enough. In some places, matter was slightly denser. In others, slightly less so. These minute imperfections became the seeds of everything we see today. As the universe expanded and cooled, those denser regions began to pull surrounding matter toward them through gravity. Dark matter, that mysterious, invisible substance that makes up about 85% of all matter in the universe, formed the scaffolding. It created gravitational wells like cosmic valleys where normal matter could collect. Hydrogen and helium atoms drifted through the darkness of space, gradually falling into these invisible traps. But here's the critical point. They didn't fall straight down. Think about water swirling down a drain. It doesn't plunge straight through the opening. Instead, it spirals, creating a vortex. The same principle applies to cosmic matter on a much grander scale. When those ancient atoms fell toward concentrations of dark matter, even the slightest sideways motion, caused by interactions with other particles, or simply because space itself wasn't perfectly symmetric, created a tiny angular momentum. And once that rotation started, there was no stopping it. This brings us to one of the most powerful principles in all of physics, the conservation of angular momentum. This law states that in a closed system, the total angular momentum remains constant unless acted upon by an external force. What does that mean in plain language? Once something starts spinning, it keeps spinning. And if that spinning object contracts, getting smaller, it spins faster, much faster. You've probably seen this principle in action during the Winter Olympics. Watch a figure skater performing a spin. When they extend their arms outward, they rotate slowly, but when they pull their arms tight against their body, they suddenly spin so fast they become a blur. The skater isn't adding energy or pushing harder. They're simply redistributing their mass closer to their center of rotation, because angular momentum must be conserved. Reducing the radius of rotation automatically increases the rotational speed. It's not magic, it's mathematics. Now picture that same principle operating on a cosmic scale. A vast cloud of gas and dust stretching across light years of space collapses under its own gravity. Even if that cloud is barely rotating at first, spinning so slowly that it would take millions of years to complete a single rotation, something extraordinary happens as it contracts. The cloud shrinks, and as it does, it spins faster, and faster, and faster still. By the time that massive molecular cloud has collapsed to form a star and a planetary system, what began as an imperceptible drift has transformed into rapid orbital motion and planetary rotation. Let me give you some perspective on just how dramatic this effect is. Imagine a cloud of gas roughly 1 light-year across, that's about 6 trillion kilometers in diameter, rotating once every million years. That's slow, incredibly slow. You wouldn't even notice the movement if you were floating inside it. But as gravity pulls that cloud inward, compressing it down to the size of our solar system, which is tiny compared to a light year, the rotation speeds up by a factor of millions. What was once a lazy drift becomes a cosmic whirlwind. Planets orbit the Sun at tens of thousands of kilometers per hour. The Sun itself rotates once every 25 days at its equator, all from that initial, barely perceptible spin. Here's where it gets even more interesting. This process doesn't create a uniform spinning ball. Instead, the collapsing cloud flattens into a disk. Why? Because of rotation itself. As the cloud spins, centrifugal effects prevent matter from falling inward along the plane of rotation as easily as it falls along the poles. Material piles up in a flat spinning disk around the forming star. We call this a protoplanetary disk, and it's where planets are born. The Atacama Large Millimeter, Submillimeter Array, ALMA for short, is a collection of 66 radio telescopes in the Chilean desert, and it's given us some of the most breathtaking views of these planetary nurseries. In 2025, astronomers using ALMA made a groundbreaking discovery. They observed a young star called Milky and its surrounding disk over a period of 7 years. By comparing images from 2017, 2019, and 2024, they created what's essentially a time-lapse video of the disk. And for the first time ever, they actually watched spiral structures within the disk twist and wind up, moving at precisely the speeds predicted by gravitational instability theory. If you're enjoying this cosmic journey, please hit that subscribe button and give this video a thumbs up. It helps more people discover these amazing stories about our universe, and it keeps me motivated to bring you more content like this. This observation of Milky was monumental because it confirmed something scientists had long suspected but never directly witnessed. Spiral arms in protoplanetary disks aren't just static features, they're dynamic, moving structures created by the disk's own gravity. These spirals might be the birthplaces of planets themselves. As the spiral arms rotate and wind tighter, they create regions of higher density where dust and gas can clump together. Over millions of years, these clumps grow, colliding and merging, eventually forming rocky cores that can attract surrounding gas to become full-fledged planets. But wait, there's more to this story. Not all planets form through the slow accumulation of dust grains. Some might form much more quickly through a process called gravitational instability. When a protoplanetary disk becomes massive enough and cold enough, portions of it can fragment directly into planet-sized objects. It's like a cosmic shortcut to planet formation. This might explain how gas giant planets can exist in wide orbits far from their parent stars, where traditional formation methods would take longer than the age of the universe. These discoveries are happening right now. The James Webb Space Telescope, humanity's most powerful observatory, launched on Christmas Day 2021, has been peering into star-forming regions that Hubble could only glimpse. In December 2024, Webb confirmed something remarkable that Hubble hinted at more than 20 years ago. Astronomers studied young stars in the small Magellanic Cloud, a dwarf galaxy neighboring our Milky Way. This galaxy is metal-poor, meaning it has low amounts of elements heavier than hydrogen and helium, similar to conditions in the early universe. What Webb found was startling. Protoplanetary disks around stars in this metal-poor environment last much longer than those in our galaxy. Some disks were still going strong around stars that were 20 to 30 million years old. That's about 10 times longer than typical disks in the Milky Way. This has profound implications. It suggests that planets could form in environments we previously thought were inhospitable. It also helps explain how planets existed in the ancient universe, forming around stars born when the cosmos was just 1 billion or 2 years old. So we've established that planets spin because they form from spinning disks, which themselves came from spinning clouds of gas. But let's zoom out and ask a bigger question. Where did those clouds get their spin in the first place? To answer that, we need to go back even further to the cosmic web itself. When astronomers map the large-scale structure of the universe, what emerges is breathtaking. Galaxies aren't scattered randomly through space. Instead, they're arranged in an intricate pattern of filaments, walls, and voids, a structure so vast it's been nicknamed the cosmic web. These filaments stretch for hundreds of millions of light-years, connecting clusters of galaxies like threads in an impossibly large tapestry. And here's the crucial detail. Matter flowing along these filaments doesn't move in straight lines. It follows curved, twisting paths carrying angular momentum with it. Think of it like this. Imagine you're looking down at a map of rivers flowing toward the ocean. The water doesn't flow in perfectly straight lines. It meanders, curves, and swirls, influenced by the terrain, gravity, and countless other factors. Each stream carries not just water, but also rotational motion. When these streams merge, their individual spins combine. The same thing happens with cosmic gas flowing through the universe. As matter streams along the filaments of the cosmic web toward dense regions where galaxies will form, it brings angular momentum with it. Those flows intersect at angles, creating torques, twisting forces that set entire regions of space spinning. Research published in recent years has shown that the angular momentum of galaxies correlates with the large-scale structure around them. Galaxies tend to spin perpendicular to the filaments they're connected to, like wheels rolling along cosmic highways. This isn't coincidence, it's a direct consequence of how matter accumulated during the universe's evolution. The spin of galaxies, and therefore the spin of everything within them, traces back to the way matter moved through space billions of years ago. Let's bring this down to Earth for a moment. Our planet rotates once every 24 hours, giving us day and night. But why does Earth spin at this particular rate? The answer lies in our planet's birth. About 4.5 billion years ago, the solar system was a swirling disk of gas and dust surrounding our newborn sun. Within that disk, tiny grains of dust collided and stuck together, gradually building up into larger and larger objects, pebbles, boulders, mountains, and eventually planet-sized bodies called planetesimals. Earth grew through countless collisions with these planetesimals over tens of millions of years. Each impact added mass, but it also added angular momentum. If a planetesimal struck Earth from a particular angle, it would either speed up or slow down our planet's rotation. The final spin rate we observe today is essentially the sum total of all those ancient impacts. But the story doesn't end there. About 4.5 billion years ago, when Earth was roughly 90% of its current size, something catastrophic happened. A Mars-sized object, scientists call it Theia, slammed into the young Earth in a cataclysmic collision. The impact was so violent that it vaporized huge portions of both worlds, throwing enormous amounts of molten rock into orbit around Earth. That debris eventually coalesced to form our moon. This giant impact didn't just create our satellite, it fundamentally changed Earth's rotation. Computer simulations suggest that before the impact, Earth might have been spinning much faster, with days lasting perhaps just 5 or 6 hours. The collision either sped up or slowed down Earth's spin. The exact effect depends on the angle and velocity of the impact, and set the stage for the Earth-Moon system we know today. And here's something fascinating. Earth's rotation is actually slowing down right now as you watch this video. The Moon's gravity creates tides in Earth's oceans, and the friction between those tidal bulges and the ocean floor gradually saps rotational energy from our planet. This means days are getting longer by about 1.5 milliseconds per century. It sounds tiny, but over geological time, it adds up. 400 million years ago, during the Devonian period, when fish were first crawling onto land, Earth's day was only about 22 hours long, and a year contained roughly 400 days. Go back even further to when the Moon first formed, and days might have lasted just 6 hours. Speaking of motion, this connects to something even more mind-blowing. Some might think we are sitting still right now, but we are actually moving through space at incredible speeds. Earth rotates at roughly 1,000 kilometers per hour at the equator. Every motion is a spin or an orbit, rotation and revolution, all the way up. If you're curious about this cosmic motion and want to understand just how fast we're truly moving, I actually made a detailed video exploring this on my video called "How Fast Are We Actually Moving Through Space?" I'll leave a link to it in the description. It really puts our cosmic journey into perspective. Now let's talk about stars. When you look up at the night sky, every star you see is rotating, but they don't all spin at the same rate. Our Sun, for instance, rotates once every 25 days at its equator, but because it's made of gas rather than solid rock, different parts rotate at different speeds. Near the poles, it takes about 35 days to complete one rotation. This differential rotation creates incredible complexity in the Sun's magnetic field, driving sunspots, solar flares, and the 11-year solar cycle that affects space weather throughout our solar system. Young stars spin much faster than old stars. When a star first ignites nuclear fusion in its core, it's rotating rapidly, sometimes completing a full rotation in just a few days or even hours. But over millions of years, stars lose angular momentum through a process called magnetic braking. The star's magnetic field interacts with the stellar wind, streams of charged particles flowing outward from the star, and this interaction acts like a brake, gradually slowing the star's rotation. By the time a star reaches middle age, like our Sun, it's spinning much more sedately. Astronomers can actually use a star's rotation rate to estimate its age, a technique called gyrochronology. It's like looking at the wrinkles on someone's face to guess how old they are, except we're measuring cosmic spin instead of skin. This method has helped scientists determine the ages of stars that would otherwise be very difficult to date, giving us crucial insights into the history of our galaxy. But some stars break this pattern spectacularly. Neutron stars, the collapsed cores left behind after massive stars explode as supernovae, take the conservation of angular momentum to an extreme. When a star with perhaps 10 times the mass of the Sun collapses down to a sphere only about 12 kilometers across, its rotation speeds up dramatically. The result is an object spinning hundreds of times per second. These rapidly rotating neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As the star spins, those beams sweep across space like a lighthouse, and if Earth happens to be in the path of that beam, we detect regular pulses of radio waves, sometimes arriving with the precision of an atomic clock. The fastest known pulsar, discovered in 2006 and designated PSRJ 1748-2446, AD, rotates an astonishing 716 times per second. That means a point on its equator is moving at roughly 25% the speed of light. At those speeds, the star's extreme gravity and rapid rotation warp space-time itself, creating effects predicted by Einstein's theory of general relativity. These objects are natural laboratories for testing physics under the most extreme conditions imaginable. And then there are black holes. When the most massive stars collapse, they don't stop at the neutron star stage. They continue collapsing until they form black holes, regions of space-time where gravity is so strong that not even light can escape. But black holes don't just have mass, they also have spin. In fact, most black holes are probably rotating at tremendous speeds, perhaps close to the theoretical maximum allowed by physics. A rotating black hole drags space-time itself around with it, an effect called frame dragging. Near the event horizon, the point of no return, space is being pulled around the black hole so violently that nothing can remain stationary. You'd be forced to move in the direction of the black hole's rotation, like being caught in a cosmic whirlpool. This region is called the ergosphere, and it's one of the strangest places in the universe. The spin of black holes isn't just a curiosity, it fundamentally affects how they behave and how they interact with their surroundings. In 1963, mathematician Roy Kerr solved Einstein's equations for a rotating black hole, and what he discovered was remarkable. Unlike a non-rotating black hole, which is relatively simple, a spinning black hole has a complex structure with multiple horizons and regions where the laws of physics manifest in bizarre ways. When material falls toward a rotating black hole, it doesn't plunge straight in. Instead, it forms an accretion disk, another spinning structure just like protoplanetary disks around young stars, but far more violent. The material in these disks reaches temperatures of millions of degrees as it spirals inward, emitting intense X-rays that we can detect across the universe. Some of the most luminous objects in the cosmos, quasars and active galactic nuclei, are powered by supermassive black holes with accretion disks. Here's where it gets even more incredible. The spin of a black hole can actually extract energy from material swirling around it. Through a process called the Penrose mechanism, proposed by physicist Roger Penrose in 1969, it's theoretically possible to harness energy from a rotating black hole. In the ergosphere, particles can split in such a way that one falls into the black hole, while the other escapes with more energy than the original particle had. The escaping particle carries away rotational energy from the black hole itself, very gradually slowing its spin. This isn't science fiction, it's permitted by the laws of physics, though we're nowhere near having the technology to actually do it. Black holes also produce jets, narrow beams of matter and energy that shoot outward from their poles at nearly the speed of light, extending for thousands or even millions of light years into space. These jets are among the most powerful phenomena in the universe, and their formation is intimately connected to the black hole's rotation and magnetic fields. The exact mechanism is still being studied, but observations from facilities like the Event Horizon Telescope, which captured the first direct image of a black hole's shadow in April 2019, are helping us understand how spin powers these cosmic engines. Let's zoom back out to galaxies themselves. Our Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms winding outward. The entire galaxy rotates, though not like a solid disk. Different parts orbit the galactic center at different speeds, creating what astronomers call differential rotation. Stars near the center complete an orbit in just a few million years, while our Sun, located about 26,000 light-years from the center, takes approximately 230 million years to make one complete circuit. That's called a cosmic year or a galactic year. Think about that for a moment. The last time our solar system was in this position in its orbit around the galaxy, dinosaurs hadn't evolved yet. The most complex life on Earth was still in the oceans. Since our planet formed 4.5 billion years ago, we've completed only about 20 orbits around the Milky Way, 20 trips around our galactic home in the entire history of Earth. It puts our existence into humbling perspective. But here's a mystery that puzzled astronomers for decades. When they measured the rotation speeds of galaxies, something didn't add up. Based on the visible matter, stars, gas, and dust, galaxies should rotate differently than they actually do. Stars far from the galactic center should be moving much slower than observed because there isn't enough visible mass to keep them moving so fast. Instead, these outer stars zip around at speeds that suggest far more mass is present than we can see. This discrepancy led to one of the most profound discoveries in modern cosmology: dark matter. In the 1970s, astronomer Vera Rubin conducted meticulous observations of galaxy rotation curves, graphs showing how fast stars orbit at different distances from the galactic center. What she found was revolutionary. The rotation curves stayed flat even at large distances from the center, rather than dropping off as expected. The only explanation was that galaxies are embedded in massive halos of invisible matter, extending far beyond the visible disk. Dark matter doesn't emit, absorb, or reflect light, which is why we can't see it directly. But we know it exists because of its gravitational effects. It makes up about 85% of all matter in the universe, and its distribution determines how galaxies rotate. The visible matter we see, stars, planets, nebulae, is basically just cosmic foam floating on an ocean of dark matter. Understanding dark matter is one of the greatest challenges in physics today, and experiments around the world are searching for these elusive particles. Galaxies themselves don't just spin in isolation, they also orbit each other. Our Milky Way is part of a collection called the Local Group, containing more than 50 galaxies. Our nearest large neighbor is the Andromeda Galaxy, located about 2.5 million light-years away. Here's something remarkable. Andromeda and the Milky Way are actually moving toward each other at about 70 kilometers per second. In approximately 4.5 billion years, our galaxies will collide and merge, creating a new, larger galaxy that astronomers have nicknamed Milkomeda. But don't worry, when galaxies collide, stars almost never actually hit each other. Space is so vast and stars are so small relative to the distances between them that the galaxies will simply pass through each other like ghosts. However, the gravitational interactions will be spectacular, flinging stars into new orbits, triggering massive bursts of star formation, and eventually settling into a new configuration. The supermassive black holes at the centers of both galaxies, Sagittarius A star in the Milky Way and the larger black hole in Andromeda, will eventually spiral together and merge, releasing gravitational waves so powerful that detectors across the universe could theoretically observe them. Speaking of gravitational waves, these ripples in space-time were predicted by Einstein in 1915, but weren't directly detected until September 14, 2015, exactly 100 years later. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the merger of two black holes, each about 30 times the mass of the Sun, located 1.3 billion light-years away. As these black holes spiraled together, they created gravitational waves that stretched and squeezed space itself. By the time those waves reached Earth, they changed the distance between LIGO's mirrors by an amount smaller than 1/10,000th the diameter of a proton. And yet we detected them. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers and neutron star collisions. Each event involves objects spinning around each other at tremendous speeds before merging. The orbital motion gets faster and faster as the objects spiral inward, until in the final moments before merger, they're circling each other hundreds of times per second. The gravitational waves encode information about their masses, spins, and orbital characteristics, allowing us to reconstruct what happened in these violent cosmic events. These discoveries have opened a new window on the universe. For all of human history until 2015, we studied the cosmos using light, first with our eyes, then with telescopes detecting different wavelengths of electromagnetic radiation. Now we can also listen to the universe through gravitational waves, detecting events that produce little or no light. It's like gaining a new sense, and it's revolutionizing our understanding of black holes, neutron stars, and the fundamental nature of gravity itself. Let's consider the smallest scales now. Does spin extend all the way down to fundamental particles? The answer is yes, with an important caveat. Electrons, quarks, and other fundamental particles have a property called spin, but it's not quite the same as planets spinning or galaxies rotating. Quantum spin is an intrinsic property like electric charge or mass. Particles don't literally rotate like tiny spheres. Instead, spin is a quantum mechanical property that has angular momentum and behaves mathematically like rotation, but emerges from the fundamental nature of quantum fields. Despite this difference, quantum spin has real, measurable effects. It determines how particles interact with magnetic fields. It's the reason magnetism exists at all. The Pauli exclusion principle, which states that two identical fermions can't occupy the same quantum state, depends on spin. This principle is why atoms have structure, why chemistry works, and ultimately why solid matter exists. Without quantum spin, you, me, and everything we see would collapse into an undifferentiated soup of particles. Quantum spin also leads to one of the strangest phenomena in physics, quantum entanglement. When two particles become entangled, measuring the spin of one instantly affects the spin of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance and thought it showed that quantum mechanics was incomplete, but experiments have confirmed that entanglement is real, and it's now being harnessed for quantum computing and quantum communication technologies. So we've journeyed from the largest structures in the universe down to the quantum realm. And everywhere we look, we find rotation, spin, and angular momentum. But let's address a question you might be wondering. Is there anything in the universe that doesn't spin? The short answer is almost nothing. Even objects that appear stationary are moving and rotating in some way. However, there are a few exceptions worth noting. The cosmic microwave background radiation, the afterglow of the Big Bang itself, shows no net rotation. If the universe as a whole was spinning, we'd expect to see a particular pattern in this ancient light, but we don't. This tells us something profound. The universe itself doesn't appear to have a preferred axis of rotation. It's expanding in all directions roughly equally without a cosmic spin. But individual structures within the universe, they almost all spin. Even interstellar gas clouds that appear diffuse and chaotic have internal motions that create net angular momentum. Comets tumble through space, asteroids rotate, dust grains spin. On Earth, even individual molecules in the air around you are rotating, vibrating, and tumbling in random directions due to thermal energy. There's something deeply beautiful about this universality of rotation. It suggests that angular momentum is as fundamental to the cosmos as energy or matter itself. In fact, angular momentum is one of the conserved quantities in physics, along with energy, linear momentum, and electric charge that arise from the symmetries of nature. According to Noether's theorem proposed by mathematician Emmy Noether in 1915, every symmetry in the laws of physics corresponds to a conservation law. The conservation of angular momentum arises from rotational symmetry, the fact that the laws of physics are the same regardless of which direction you're facing in space. This connection between symmetry and conservation laws is one of the most elegant insights in all of physics. It tells us that the universe has an underlying mathematical harmony, and that the persistence of spin from galaxies to atoms isn't just a coincidence. It's baked into the fundamental structure of reality. Now let's talk about something that challenges our intuition. Not everything in the universe spins in the same direction. While individual systems like our solar system have a preferred direction, with most planets orbiting the Sun in the same direction and rotating the same way, the universe as a whole shows no preference. About half of all galaxies spin clockwise from our perspective, and half spin counterclockwise. This is exactly what we'd expect from a universe born from quantum fluctuations with no inherent directionality. However, there are fascinating exceptions even within our solar system. Venus rotates backward compared to most planets, a phenomenon called retrograde rotation. Instead of rotating in the same direction it orbits the Sun, Venus spins the opposite way. A day on Venus, one complete rotation, takes 243 Earth days, which is actually longer than a Venusian year of 225 Earth days. This means that on Venus, a day is longer than a year. Even stranger, the sun rises in the west and sets in the east. What caused Venus to spin backward? The most likely explanation is a massive collision or series of collisions early in the solar system's history. Just as the moon-forming impact altered Earth's rotation, one or more giant impacts could have flipped Venus upside down or slowed its rotation so much that tidal forces from the sun eventually reversed it. Computer simulations show that planetary collisions were common in the early solar system, when leftover planetesimals were still scattered throughout the inner planet's orbits. Uranus presents another oddity. While most planets have their rotation axes roughly perpendicular to their orbital planes, meaning they spin more or less upright, Uranus is tilted 98 degrees. It essentially rolls around the sun on its side like a barrel. This extreme tilt means that Uranus experiences the most dramatic seasons in the solar system. Each pole gets 42 years of continuous sunlight, followed by 42 years of darkness. Again, the most plausible explanation is a collision with an Earth-sized object during the planet's formation. These examples remind us that while the general pattern of spin in the universe follows predictable rules, individual histories matter. The cosmos is not a perfectly ordered clockwork, but a dynamic, chaotic system where violence and chance play significant roles. Every object's current spin state tells a story of its formation and evolution, of collisions survived and gravitational encounters endured. Let's zoom back out to consider galaxy clusters, the largest gravitationally bound structures in the universe. These are collections of hundreds or thousands of galaxies held together by their mutual gravity and embedded in enormous clouds of hot gas. The Coma cluster, for example, contains over 1,000 identified galaxies and lies about 320 million light-years from Earth. Do these clusters rotate? The answer is yes, but very slowly. The individual galaxies within clusters have their own motions, orbiting the cluster's center of mass in complex crisscrossing paths. But the cluster as a whole can have a net rotation. This rotation is extremely slow. It might take tens of billions of years for a cluster to complete one rotation, but it's there, and it provides clues about how these massive structures formed. Recent simulations of cosmic structure formation show that galaxy clusters acquire their angular momentum from the same process that spins up galaxies, the twisting, turning flows of matter along the cosmic web's filaments. As matter streams into the growing cluster from different directions, the net angular momentum doesn't cancel out completely. The result is a slow, stately rotation that will continue for as long as the cluster exists. But the universe is expanding, driven by dark energy, a mysterious force causing the expansion of space to accelerate. As space stretches, galaxy clusters are getting farther apart. Eventually, in the unimaginably distant future, clusters will become isolated islands in an ever-expanding void. The expansion will separate clusters so much that light from other clusters will no longer reach us. Civilizations in that distant epoch will look out at a dark, empty universe, with only their own cluster visible, a lonely collection of galaxies spinning in isolation. Within those isolated clusters, however, spin will persist. Stars will continue orbiting their galaxies' centers. Planets will keep rotating and revolving around their stars. Black holes will still spin. Angular momentum, once imparted, has nowhere to go in the vacuum of space. Unlike objects on Earth, which slow down due to friction with air or surfaces, cosmic objects face almost no resistance. Tidal forces can transfer angular momentum between objects, but they can't make it disappear. Let me give you an example of just how persistent cosmic spin can be. The pulsar I mentioned earlier, PSR J1 748-24446 AD, spinning 716 times per second, is part of a globular cluster called Terzan 5, located about 19,000 light-years away. This cluster is ancient, probably over 12 billion years old, formed when the universe itself was less than 2 billion years old. That pulsar, or rather the massive star that collapsed to form it, has been carrying angular momentum for most of the universe's history. Even in its collapsed state as a neutron star, it will continue spinning for billions or even trillions of years, gradually slowing through the emission of electromagnetic radiation, but never truly stopping. This persistence of spin has practical consequences. Engineers designing spacecraft must account for the rotation of Earth, the orbital motion of our planet around the Sun, and even the motion of the solar system through the galaxy when calculating trajectories for interplanetary missions. The rotation of Earth means that launching eastward in the direction of Earth's spin provides a speed boost, which is why most spaceports are located as close to the equator as possible and launched toward the east. NASA's Kennedy Space Center in Florida, the European Spaceport in French Guiana, and the Satish Dhawan Space Center in India are all positioned to take advantage of Earth's rotation. At the equator, Earth's surface moves eastward at about 1,000 kilometers per hour. A rocket launched eastward gets that velocity for free, reducing the fuel needed to reach orbit. It's a direct, practical benefit of our planet's spin, a 4.5 billion-year-old rotation helping us reach for the stars. The rotation of Earth also creates another crucial phenomenon, our magnetic field. Deep beneath your feet, about 1,800 kilometers down, lies Earth's outer core, a churning ocean of molten iron and nickel at temperatures exceeding 9,000 degrees Fahrenheit. This liquid metal doesn't just sit there, it flows in complex patterns driven by Earth's rotation and heat escaping from the planet's interior. These flowing currents of electrically conductive material generate electric currents, which in turn produce magnetic fields. The result is a planetary-scale dynamo that creates Earth's protective magnetic shield. This magnetic field extends tens of thousands of kilometers into space, forming the magnetosphere. It's invisible, but absolutely vital for life. The magnetosphere deflects most of the charged particles streaming from the Sun in the solar wind. Without this protection, those particles would strip away Earth's atmosphere over millions of years, just as happened on Mars after its magnetic field shut down billions of years ago. Every time you use a compass, you're tapping into a phenomenon ultimately powered by Earth's rotation and the convection patterns it creates in our planet's liquid core. Other planets with significant magnetic fields, Jupiter, Saturn, Uranus, and Neptune, generate them through similar dynamo processes. Jupiter's magnetic field is the strongest in the solar system, about 20,000 times more powerful than Earth's. This enormous field is generated by metallic hydrogen deep within Jupiter's interior, where hydrogen is compressed so intensely that it behaves like a liquid metal. Jupiter rotates incredibly fast, once every 10 hours, and this rapid spin drives powerful convection currents that create the massive magnetic field. Jupiter's rotation also creates the most dramatic weather in the solar system. The Great Red Spot, a storm larger than Earth that's been raging for at least 350 years, is ultimately powered by the planet's rapid rotation and internal heat. The rotation creates strong Coriolis forces, the same forces that cause hurricanes on Earth to spin. On Jupiter, these forces combine with rising heat to create stable, long-lasting storm systems that dwarf anything we experience on our planet. Speaking of the Coriolis effect, this is another direct consequence of planetary rotation that affects our daily lives. When objects move across Earth's rotating surface, they appear to curve from the perspective of someone standing on the ground. In the northern hemisphere, moving objects deflect to the right, in the southern hemisphere, to the left. This effect shapes weather patterns, ocean currents, and even the direction water drains. though the popular myth about toilets flushing in opposite directions in different hemispheres is exaggerated. The Coriolis effect is real and important for large-scale systems, but your bathtub is far too small for it to matter. Hurricanes and typhoons owe their spinning structure to the Coriolis effect. Warm, moist air rises near the ocean's surface, creating a low-pressure area. Surrounding air rushes in to fill the void, but Earth's rotation deflects this inrushing air, causing it to spiral. In the northern hemisphere, hurricanes rotate counterclockwise. In the southern hemisphere, cyclones rotate clockwise. These massive rotating storms can be hundreds of kilometers across and last for weeks, all because our planet spins beneath them. The Coriolis effect also drives ocean currents. The Gulf Stream, which carries warm water from the tropical Atlantic up the eastern coast of North America and across to Europe, exists because of the interaction between wind patterns, temperature differences, and Earth's rotation. This current moderates climate across vast regions, making Western Europe much warmer than it would otherwise be at its latitude. Without Earth's rotation creating the Coriolis effect, our oceans would circulate completely differently, and Earth's climate would be almost unrecognizable. Let's return to stars for a moment and consider their life cycles. When a massive star, say 20 times the mass of the Sun, exhausts the nuclear fuel in its core, it can no longer support itself against gravity. The core collapses catastrophically in less than a second, and the outer layers rebound in a supernova explosion so bright it can briefly outshine an entire galaxy. The explosion scatters heavy elements, carbon, oxygen, iron, gold, uranium, across space. These are the elements forged by nuclear fusion in the star's core and during the explosion itself. Here's the connection to spin: that ejected material doesn't fly out uniformly in all directions. The star's rotation, magnetic fields, and asymmetries in the collapse create jets and preferential directions. Observations of supernova remnants, the expanding shells of gas left behind after the explosion, show complex structures with filaments, knots, and asymmetries. Some of this structure comes from the star's rotation before it died. The neutron star or black hole left behind inherits most of the original star's angular momentum, but compressed into an object millions of times smaller. This is why neutron stars spin so fast. But the ejected material also carries angular momentum outward. That gas, enriched with heavy elements, eventually becomes part of new molecular clouds where future stars will form. Those new stars inherit some of the angular momentum from the supernova debris. In this way, spin is recycled through generations of stars, passing from one stellar generation to the next across billions of years. Our own solar system formed from such enriched material. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe were created in stars that lived and died before our sun was born. Those ancient stars were spinning. Their rotation influenced how they evolved, how they died, and how their ashes spread through space. You are made of stardust, and that stardust carries the legacy of cosmic rotation stretching back to the universe's beginning. This brings us to a profound question. Could the universe itself have been born spinning? For decades, astronomers have searched for evidence of overall rotation in the universe. If the Big Bang somehow imparted a net angular momentum to the cosmos, we'd expect to see patterns in the distribution of galaxies or in the cosmic microwave background radiation. But every careful analysis has found no evidence for universal rotation. The cosmos appears to expand equally in all directions, without a preferred axis. However, the absence of universal rotation doesn't mean the early universe was perfectly symmetric. Quantum fluctuations during the inflationary epoch, a period of exponentially rapid expansion in the first fraction of a second after the Big Bang, created tiny density variations. These variations, stretched to cosmic scales by inflation, became the seeds of all structure: galaxies, clusters, superclusters, the cosmic web itself. And embedded in those fluctuations were random orientations and motions that eventually became the angular momentum we observe in every spinning object today. Think of it this way. The universe started in a state of incredible symmetry and simplicity. But quantum mechanics ensures that nothing is perfectly smooth or uniform at small scales. Those quantum jitters, amplified by cosmic expansion, broke the symmetry and introduced variations. As matter clumped together under gravity, those variations translated into motion, and motion at angles translates into spin. The universe didn't need to be born spinning for everything in it to end up rotating. The very nature of quantum mechanics and gravity working together over cosmic time naturally produces angular momentum. Recent observations have given us tantalizing glimpses into the early universe's structure. The James Webb Space Telescope, with its ability to peer deeper into space and further back in time than any previous observatory, has been finding galaxies that existed when the universe was only a few 100 million years old. These ancient galaxies were already rotating, already forming stars, already exhibiting the basic structures we see in galaxies today. This tells us that the processes that create spin and structure work quickly on cosmic timescales. One particularly exciting discovery came from observations of galaxy SMMJ 2135-0-102, a massive galaxy that existed when the universe was only about 1.5 billion years old, roughly 10% of its current age. Despite its youth, this galaxy was already rotating in an organized way, with a disk structure similar to spiral galaxies we see today. This suggests that the mechanisms that create rotating disks operated efficiently even in the early universe. These observations challenge some of our assumptions about how galaxies form and evolve. Traditional models suggested that early galaxies should be chaotic and irregular, with organized rotating structures developing only gradually over billions of years. But observations keep finding mature-looking galaxies at surprisingly early times. This doesn't mean our models are completely wrong. It means the universe is more complex and fascinating than we thought. The processes that create rotation and structure can work faster and more efficiently than we expected. This is one of the wonderful things about science. It's self-correcting. When observations contradict predictions, we don't ignore the data. We refine our theories, develop new models, and deepen our understanding. The discovery of unexpectedly mature early galaxies has sparked intense research into the conditions in the early universe, the efficiency of star formation, and the role of dark matter in shaping galaxy formation. Each answer raises new questions, propelling us forward. Let's consider the role of magnetic fields in cosmic rotation. Magnetism and rotation are intimately connected throughout the universe. Moving electric charges create magnetic fields, and magnetic fields influence how charged particles move. In the ionized gas that fills much of space, this connection becomes crucial. When gas collapses to form stars or accretion disks, magnetic fields threading through the gas can transport angular momentum outward, allowing material to fall inward despite conservation of angular momentum. This process is called magnetic braking, and it's essential for star formation. Without some way to shed angular momentum, collapsing gas clouds would spin faster and faster as they contracted, eventually spinning so fast that centrifugal forces would halt the collapse entirely. Stars would never form, but magnetic fields provide an escape valve. They couple to the gas and transfer angular momentum to outer regions, or launch it away in bipolar jets, allowing the inner regions to continue collapsing. When you look at images of stellar nurseries like the Eagle Nebula, home to the famous pillars of creation, what you're seeing is this process in action. Within those dark pillars of dust and gas, protostars are forming, spinning as they contract. Many launch jets from their poles, visible as bright streamers extending for light years. Those jets carry away angular momentum and also clear out surrounding material, eventually revealing the newborn star. The Hubble Space Telescope and now the James Webb Space Telescope have captured exquisite images of these jets, allowing astronomers to study the intricate dance between rotation, magnetism, and starbirth. Magnetic fields also play a crucial role in galaxy-scale processes. Galaxies have magnetic fields permeating their disks and halos, generated by dynamo processes similar to those in planets, but on vastly larger scales. These fields are stretched and twisted by the galaxy's rotation, creating complex patterns. They influence how gas moves within galaxies, how cosmic rays propagate, and even how stars form. Radio telescopes can map these magnetic fields by detecting the polarization of radio waves emitted by galaxies, revealing beautiful spiraling structures aligned with the galaxy's rotation. The interplay between rotation and magnetism extends to the most extreme objects, magnetaires. These are neutron stars with magnetic fields trillions of times stronger than Earth's, so intense that the magnetic field itself warps the star's crust and generates seismic activity. Magnetars occasionally produce bursts of X-rays and gamma rays when their crusts crack and magnetic field lines reconnect explosively. These starquakes release more energy in a fraction of a second than our Sun emits in thousands of years. Magnetars rotate too, though typically slower than regular pulsars, once every few seconds rather than hundreds of times per second. The extreme magnetic field is thought to be generated during the neutron star's birth, when the collapsing stellar core creates powerful dynamo conditions. As the magnetar ages and its rotation slows, the magnetic field gradually decays over thousands of years. These objects represent an extreme regime where rotation, magnetism, and gravity all reach their most intense expressions. Now let's talk about something that might seem counterintuitive. Rotation can actually create gravity, or at least something that looks like gravity. In rotating reference frames, objects experience centrifugal force, pushing them outward. From the perspective of someone in that rotating frame, this feels just like gravity pulling in the opposite direction. This principle could theoretically be used to create artificial gravity in spacecraft. If you've seen science fiction movies with rotating space stations, you've seen this idea in action. A large wheel-shaped station rotating around its axis would create centrifugal force, pushing objects toward the outer rim. Astronauts walking on that rim would feel pressed against the floor, experiencing artificial gravity proportional to the rotation rate and the station's radius. This isn't just fiction, it's basic physics, and it's one of the most practical ways to create artificial gravity for long-duration space missions. The space station would need to be fairly large and rotate at the right speed to create comfortable artificial gravity without excessive Coriolis effects that might cause disorientation. Engineers have designed concepts for such stations since the early space age. The Stanford Torus, proposed in 1975, was a design for a space habitat 1 mile in diameter that would rotate once per minute, creating Earth-like gravity on its inner rim and housing 10,000 people. While we haven't built anything on that scale yet, smaller rotating spacecraft could be developed for missions to Mars or other destinations requiring months or years in space. The rotation of massive objects also affects space-time itself through frame dragging, which I mentioned earlier with black holes. But this effect isn't limited to black holes. Any rotating mass drags space-time around it, just much more weakly. Earth's rotation creates frame dragging that was actually measured by the Gravity Probe B satellite launched in 2004. After years of painstaking data analysis, scientists confirmed that Earth's rotation does indeed drag space-time around with it, exactly as Einstein's general relativity predicted. The effect is tiny. Satellites orbiting Earth experience their orbital planes shifted by only about 39 milliseconds per year due to frame dragging. That's about the width of a human hair viewed from 5 kilometers away. But the fact that we can measure such a minuscule effect is a testament to human ingenuity and our determination to test the fundamental laws of physics. It also confirms that rotation isn't just motion through space, it's woven into the very fabric of space-time itself. Let's think about time for a moment. Rotation creates time on human scales. Our days exist because Earth rotates, our years because Earth revolves around the Sun. But rotation also affects time in more fundamental ways through relativity. According to special relativity, time passes slower for objects moving at high speeds. On a rotating object, different parts move at different speeds. The edge moves faster than points closer to the axis. This means time literally runs at different rates at different locations on a spinning object. For Earth, this effect is tiny but measurable. Atomic clocks at the equator, where Earth's surface moves at 1,000 kilometers per hour, tick slightly slower than identical clocks at the poles. You age ever so slightly faster if you live at the North Pole compared to living on the equator, though the effect is so small that you'd never notice it. Over a human lifetime, we're talking about a difference measured in billionths of a second. But for objects rotating at relativistic speeds, significant fractions of light speed, these time dilation effects become dramatic. On a neutron star spinning hundreds of times per second, with its equator moving at perhaps 10 or 20% of light speed, time at the equator passes noticeably slower than at the poles. For observers watching from a distance, events at the equator would appear to happen in slow motion compared to events at the poles. This is one of the ways that extreme rotation reveals the relativity of time itself. Black holes take this to the ultimate extreme. Near a rapidly spinning black hole, space-time is twisted so severely that time and space themselves get mixed up in ways that defy everyday intuition. Inside the ergosphere, the region I mentioned earlier, it becomes impossible to remain stationary. Space itself is being dragged around the black hole so forcefully that everything, even light, must orbit in the direction of the black hole's rotation. You could fire your rocket engines at full power trying to hover in place, and you'd still be dragged around the black hole. Space itself is in motion. This leads to one of the strangest predictions of general relativity: closed, time-like curves. In the mathematical solutions describing rotating black holes, there exist paths through space-time that loop back on themselves. Follow one of these paths, and you'd return to your starting point not just in space, but also in time you'd arrive before you left. These are potential time machines, at least mathematically. Whether they actually exist in nature and whether the laws of physics would permit their use remains one of the deepest mysteries in theoretical physics. Most physicists suspect that quantum effects or other mechanisms we don't yet understand would prevent closed time-like curves from forming or being traversable. The universe seems to protect causality, the principle that causes must precede effects. But the fact that rotation in general relativity even allows for such possibilities shows just how profoundly spin affects the structure of reality. Let's bring things back to more familiar territory. The rotation of Earth has been gradually slowing throughout our planet's history due to tidal interactions with the Moon. When Earth formed 4.5 billion years ago, a day was only about 6 hours long. Our planet spun much faster then, but the Moon's gravity raises tides in Earth's oceans, and the friction of those tides sloshing around dissipates energy, gradually slowing Earth's rotation. The angular momentum doesn't disappear, it's transferred to the Moon, which slowly spirals outward, moving about 1.5 inches farther from Earth each year. This means that days are getting longer by about 1.7 milliseconds per century. It doesn't sound like much, but it adds up. 600 million years ago, during the Ediacaran period, when the first complex multicellular life was appearing in Earth's oceans, a day was only about 22 hours long, and a year contained about 400 days. Paleontologists have actually confirmed this by studying growth rings in ancient corals and stromatolites, which show daily and seasonal patterns. These fossils are natural clocks preserving the rhythm of Earth's rotation from hundreds of millions of years ago. Eventually, billions of years in the future, Earth's rotation will slow until one side perpetually faces the Moon, just as the Moon already keeps one face toward Earth. At that point, Earth and Moon will be tidally locked to each other, with Earth's rotation period matching the Moon's orbital period, though by then, both will be much longer than they are now, perhaps 50 or 60 of our current days. However, this tidally locked state won't last forever. The Sun's increasing brightness over billions of years will eventually evaporate the oceans, change Earth's tidal dynamics, and ultimately engulf both Earth and Moon as the Sun expands into a red giant star in about 5 billion years. But before that dramatic end, the Sun's rotation will also evolve. Like all stars, the Sun is slowly losing angular momentum through its solar wind, a stream of charged particles flowing outward from its surface. The Sun's magnetic field gets dragged along with this wind, and that carries away rotational energy. Young stars like the Sun rotate much faster than older ones. When the Sun formed, it probably rotated once every few days. Now it takes about 25 days to complete one rotation at its equator, and about 35 days near its poles. Yes, the Sun rotates at different rates at different latitudes because it's not solid. It's a ball of plasma where different layers can rotate independently. This differential rotation, faster at the equator than the poles, is actually what drives the Sun's magnetic field and the 11-year solar cycle. The Sun's magnetic field lines get twisted and tangled by the differential rotation, building up magnetic energy until it explosively releases in solar flares and coronal mass ejections. These events can send billions of tons of plasma hurtling toward Earth at millions of kilometers per hour. When this material hits Earth's magnetosphere, it can trigger geomagnetic storms that create beautiful auroras, but can also disrupt satellites, power grids, and communication systems. The most powerful geomagnetic storm in recorded history, the Carrington event of September 1859, occurred when a massive solar eruption struck Earth's magnetic field. Telegraph systems worldwide went haywire, with some operators receiving electric shocks and telegraph paper catching fire from the induced currents. Auroras were seen as far south as the Caribbean. If a similar event happened today, the damage to our technology-dependent civilization could be catastrophic, potentially causing trillions of dollars in damage and taking years to repair. These solar storms are ultimately powered by the Sun's rotation and the magnetic fields it generates. Every 11 years or so, the Sun's magnetic field completely reverses. North becomes south and south becomes north as part of a cycle driven by the internal dynamo processes linked to rotation. We're still working to fully understand the complex physics involved, but rotation is clearly central to how our star behaves. Other stars show even more dramatic rotation-driven activity. Young T Tauri stars, infant stars still contracting toward the main sequence, rotate rapidly and have enormous star spots covering significant fractions of their surfaces. These spots are like giant versions of sunspots, regions where strong magnetic fields emerge from the star's interior and suppress convection, creating cooler, darker areas. On some T Tauri stars, spots can cover 20 or 30% of the visible surface, compared to less than 1% for large sunspot groups on our Sun. These young stars also produce powerful stellar flares thousands of times more energetic than the largest solar flares. The rapid rotation and strong magnetic fields combine to create intense magnetic activity. Any planets forming around such stars would be subjected to fierce radiation and stellar wind, potentially affecting their atmospheres and habitability. Understanding how stellar rotation and magnetic activity evolve over time is crucial for understanding where life might arise elsewhere in the galaxy. Now let's zoom out and consider rotation on cosmological scales. Galaxy superclusters, collections of many galaxy clusters containing tens of thousands of galaxies, are the largest clearly defined structures in the universe. These superclusters are hundreds of millions of light-years across. Do they rotate? The answer appears to be barely, if at all. At these enormous scales, the expansion of the universe becomes dominant. Galaxy superclusters aren't gravitationally bound, they're being pulled apart by cosmic expansion. Any rotation they might have is overwhelmed by this expansion. However, computer simulations of cosmic structure formation show that even superclusters acquire tiny amounts of angular momentum from the asymmetric flows of matter during their formation. In principle, they rotate, but the rotation is so slow and the structures are being pulled apart so rapidly that the rotation is almost irrelevant. In the distant future, as dark energy continues to accelerate cosmic expansion, these structures will be completely dispersed. Their minimal rotation will become a footnote in cosmic history. This brings up an interesting point. Rotation becomes less important at larger scales. On human scales, Earth's rotation dominates our experience of time and space. On planetary scales, rotation shapes orbits and creates magnetic fields. On stellar scales, rotation drives activity and evolution. On galactic scales, rotation defines structure, but on the largest cosmological scales, expansion takes over. The universe itself doesn't rotate, it expands. And that expansion, driven by dark energy, will ultimately dilute and disperse even the grandest rotating structures. Yet rotation will persist wherever matter remains concentrated. Billions of years from now, long after the last stars have formed from the last available gas, long after galaxies have consumed their fuel, stellar remnants will continue spinning. White dwarfs will rotate, neutron stars will spin, black holes will possess angular momentum. These spinning corpses will be among the last complex objects in a universe growing ever darker, colder, and emptier. In the unimaginably distant future, 10 to the 100 years or more, even black holes will evaporate through Hawking radiation, a quantum mechanical process where particle-antiparticle pairs form at the event horizon, with one particle escaping while the other falls in. This slowly drains the black hole's mass and energy. As a black hole evaporates, it also loses angular momentum, carried away by the radiation it emits. Eventually, even the last supermassive black holes will vanish, taking their angular momentum with them. What happens to angular momentum when a black hole finally evaporates? This is one of the fascinating questions at the intersection of quantum mechanics and general relativity, two theories that have yet to be fully reconciled. The evaporation process must conserve angular momentum, just as it conserves energy and electric charge. The radiation leaving the black hole must carry away spin information encoded in the quantum properties of the emitted particles. But the details of exactly how this works remain an area of active research and intense debate among theoretical physicists. Some versions of quantum gravity suggest that information, including information about angular momentum, might be preserved in subtle correlations in the Hawking radiation. Others propose that black hole remnants, tiny, stable objects containing the compressed information of everything that fell into the original black hole, might persist after evaporation. These remnants would preserve the angular momentum like microscopic spinning quantum objects. We simply don't know yet. Answering this question definitively will require a complete theory of quantum gravity, something physicists have been pursuing for decades. Let's return to more immediate timescales and consider the future of humanity's relationship with cosmic rotation. As we venture farther into space, understanding and harnessing rotation will become increasingly important. Spacecraft already use spinning reaction wheels and gyroscopes for attitude control. Changing the spin rate of these wheels allows the spacecraft to rotate without expelling propellant. This technology enabled the Hubble Space Telescope to point with extraordinary precision and allows satellites to orient their solar panels and antennas with incredible accuracy. Future spacecraft might use rotating sections to provide artificial gravity for crews on long-duration missions. Imagine a spacecraft traveling to Mars with a slowly rotating habitat module. Astronauts could live in Earth-like gravity during the 6-month journey, avoiding the muscle atrophy and bone loss associated with prolonged weightlessness. The engineering challenges are significant: rotating joints, differential rotation between modules, gyroscopic effects, but all solvable with current technology. It's largely a question of resources and commitment. We might even build rotating space habitats in orbit, as I mentioned earlier, with concepts like the Stanford Torus. These could serve as permanent settlements, research stations, or staging points for deeper space exploration. Living on the inner surface of a rotating cylinder or torus, residents would experience artificial gravity indistinguishable from the real thing. They could walk, run, and pour water normally, all thanks to centrifugal force from rotation. These habitats could orbit Earth, the Moon, or Mars, or float freely in space at strategic locations like the Earth-Moon Lagrange points. Rotation might also provide solutions for generating power in space. A tethered satellite system with two masses connected by a cable spinning around their common center of mass could generate electricity as the conductive tether passes through Earth's magnetic field. This concept, called an electrodynamic tether, has been tested on a small scale and could theoretically provide both power generation and propulsion for spacecraft. It's another example of how understanding and exploiting rotation and angular momentum opens new possibilities. Even our search for life elsewhere in the universe must consider rotation. The habitable zone around a star, the region where liquid water could exist on a planet's surface, depends partly on planetary rotation. A planet that rotates too slowly might have one side perpetually scorched, while the other freezes. Earth's 24-hour rotation period distributes solar heat relatively evenly, preventing extreme temperature variations that would make life much more difficult. When astronomers search for potentially habitable exoplanets, rotation rate is one of many factors they consider. Tidal locking is particularly important here. Many exoplanets orbit very close to their stars, especially planets around small red dwarf stars, which are the most common stars in the galaxy. These close-in planets often become tidally locked, with one side always facing the star and the other in perpetual darkness. For a long time, scientists thought such planets couldn't support life. The day side would be too hot, the night side too cold, and any atmosphere might freeze out on the dark side and collapse. But recent climate models suggest that atmospheres on tidally locked planets could redistribute heat from the day side to the night side through winds and currents, potentially creating a ring of habitable conditions around the planet's terminator, the boundary between day and night. Some models even suggest that perpetual twilight conditions might be uniquely suited to certain forms of life. This means rotation, or the lack thereof, doesn't necessarily preclude habitability. It just creates different conditions that life might adapt to in unexpected ways. Consider also the rotation of the galaxy and its role in the emergence of life. Our solar system orbits the Milky Way's center once every 230 million years, a period sometimes called a cosmic year. Over Earth's 4.5 billion year history, our planet has completed about 20 cosmic years. As we orbit, we pass through the galaxy's spiral arms, regions of enhanced star formation where massive stars live fast and die young in spectacular supernovae. These cosmic events could have influenced life on Earth through increased radiation or by triggering climate changes through various mechanisms. Some researchers have proposed that mass extinction events on Earth might correlate with passages through spiral arms or disturbances from close encounters with other stars or molecular clouds. The evidence is controversial and debated, but it raises fascinating questions about how galactic rotation and our position in the galaxy might influence the development of life over geological time. Our journey around the galaxy is not just a scenic, cosmic tour. It places us in different environments that might have profound effects. The rotation of the galaxy also determines which stars we might someday reach. Stars don't orbit the galaxy in fixed positions relative to each other. They have their own orbital velocities that differ from their neighbors. Over thousands or millions of years, nearby stars drift apart while formerly distant stars draw closer. Proxima Centauri, currently our nearest stellar neighbor, at 4.2 light-years away, will remain close for a few thousand more years before drifting farther away. Other stars will take its place as our nearest neighbors. This cosmic reshuffling, driven by galactic rotation and the individual orbits of hundreds of billions of stars, means that the map of nearby space is constantly changing. Any civilization contemplating interstellar colonization must account for stellar motions. The stars accessible to a civilization change over time, creating a dynamic rather than static picture of the galactic neighborhood. This adds another layer of complexity to questions about the possibility of encountering other civilizations. Not only must they exist and develop technology at the right time, but they must also be in the right place along their respective galactic orbits. Speaking of other civilizations, the rotation of the galaxy might actually hinder contact between intelligent species. The vast distances between stars are already daunting, but add in the motion of stars in their galactic orbits, and coordinating meetings becomes even more challenging. Two civilizations might rise and fall on opposite sides of the galaxy, never knowing the other existed. Even civilizations in relatively nearby star systems face the problem that by the time a radio signal travels between them, both stars have moved to new positions in the galaxy. The rotation and expansion of the universe create what's known as the cosmic light cone, the region of space-time from which light has had time to reach us since the Big Bang. Beyond that cone lies the unobservable universe, which might be infinite in extent. If other civilizations exist in regions of space beyond our cosmic light cone, we can never interact with them, even in principle. The expansion of space ensures that light from those regions will never reach us. The universe's structure, shaped by expansion and rotation on various scales, fundamentally limits who can contact whom. This isolation might seem depressing, but it also means that life, wherever it emerges, gets to develop and evolve in its own unique way, shaped by local conditions rather than homogenized by contact with other civilizations. The rotation of galaxies, the orbital motions of stars, and the expansion of the universe create a cosmos of islands, regions where life and intelligence can develop independently, exploring different solutions to the challenges of existence. Each island tells its own story, spins its own tale. And what tales they must be. Across the universe, on planets orbiting stars we'll never see, in galaxies whose light will never reach Earth, other worlds must be spinning. Some rotate rapidly, creating fierce winds and extreme seasons. Others turn slowly, baking one hemisphere while freezing the other. Some have multiple moons, creating complex tidal patterns. Others orbit binary stars, experiencing double sunsets and intricate gravitational dances. Each rotating world is unique, shaped by its particular history of collisions, tidal interactions, and orbital evolution. On some of those worlds, perhaps, intelligent beings have emerged and looked up at their spinning skies, wondered about the motions they observe, and sought to understand why everything turns. They might have developed their own physics, their own mathematics, their own language to describe rotation and angular momentum. And they, like us, would discover that spin is universal, that from the smallest quantum particles to the largest galactic structures, everything participates in the cosmic dance of rotation. This universality points to something profound about the nature of reality. Rotation isn't just a phenomenon that happens to occur in our universe. It's deeply embedded in the mathematical structure of physical law. The conservation of angular momentum follows from the rotational symmetry of space, the fact that the laws of physics don't depend on which direction you call up. This connection between symmetry and conservation is one of the most beautiful insights in all of science, suggesting that the universe operates according to deep mathematical principles that we're only beginning to fully appreciate. As we look to the future, our understanding of rotation will continue to deepen. Gravitational wave observatories like LIGO and the future space-based LISA mission will detect ripples in space-time from merging black holes, revealing their spins and how those spins affect the merger dynamics. New telescopes will observe ever more distant galaxies, showing us how rotation evolves over cosmic time. Quantum computers might help us understand spin at the most fundamental level, potentially leading to technologies we can barely imagine today. Closer to home, we'll continue to refine our understanding of Earth's rotation and how it's changing. Climate change is actually affecting Earth's spin. The melting of ice sheets and redistribution of water mass alters the planet's moment of inertia, slightly changing the length of the day. Scientists monitor Earth's rotation with extraordinary precision using techniques like very long baseline interferometry, which can detect changes in day length of less than a millisecond. This precision is necessary for GPS systems, astronomical observations, and understanding Earth's internal dynamics. Everything spins, Josue, from electrons to galaxy superclusters, from planets to pulsars, from hurricanes to black holes. Rotation is woven into the fabric of existence, a fundamental expression of how the universe works. It shapes time and space, generates magnetic fields, determines habitability, enables life, and drives the evolution of everything we observe. When you look up at the night sky and see stars wheeling overhead, you're witnessing the combined rotations of Earth, the Sun through the galaxy, and the individual motions of distant stellar systems, layers upon layers of spin, each telling part of the cosmic story. And you, standing on this spinning world made of atoms whose electrons spin, orbiting a rotating star, in a rotating galaxy, in an expanding universe, you are part of that story. Every breath you take, every moment you experience unfolds on a stage that is itself in constant motion, turning, spinning, dancing through the cosmos. In understanding why everything spins, we understand something fundamental about existence itself. We see that motion, change, and transformation are not aberrations but the very nature of reality. If you made this far, make sure to give this video a like. And if the cosmic scales explored here left you pondering humanity's place in this vast, spinning universe, you might find the video on the screen fascinating. Why the universe makes it impossible for any two civilizations to ever meet. Discover how the very structure of space-time, cosmic expansion, and the immense scales involved create barriers that might forever separate intelligent species, even in a universe teeming with life. See you there.